Thanks. Thanks very much for the invitation. Just some quick things. I am viewing the chat if you have any questions about the chat. If you have any questions, just put them in the chat. And also feel free to interrupt with questions. And, you know, it's a slide talk. So if you miss something in a slide, I'm very happy to go back to previous slides. And there are even similar slides to this on my website. So you can find the slides there too, if you want to look. Okay, but anyways, please ask a lot of questions. So I want to tell you about some recent work, and the work builds on a story that goes back to some beautiful work of Fati from the 70s, which I want to tell you about. So I want to start my talk off by telling you about this formula, this result. So the theorem of Fati, it's actually more general than this, but already the special case is quite interesting, involves the group of volume-preserving homeomorphisms of the n-disk that are the identity near the boundary. So it's very important in this talk that we're talking about homeomorphisms rather than diffeomorphisms. This condition of being the identity near the boundary, people call this being compactly supported. So you can think of this as the group of compactly supported volume-preserving homeomorphisms of the n-disk. Maybe if you haven't seen a volume-preserving homeomorphism before, all I mean is that if I take an open set and then I look at where it goes under my homeomorphism, then where it goes has the same volume as where it started. And what Fati showed in the 70s is that this is a simple group, say in the disk case, as long as the dimension is at least 3. And if you're not so used to seeing these kind of questions, simple just means that there are no non-trivial proper normal subgroups. And one reason we are interested in this is if a group is simple, then it has no quotient groups. If it does have a normal subgroup, an interesting normal subgroup, I can take its quotient and I can get a new group. Another remark I want to make along the lines of simplicity is you might wonder, why are we studying this group of compactly supported transformations? Well, if I studied the full group just of volume-preserving homeomorphisms, and that group definitely would not be simple because the compactly supported ones form a normal subgroup of the full group. So that's our motivation for studying these compactly supported ones, at least from the point of view of this simplicity question. Well, so there's a natural question that arises from this work, which is what happens in the two-dimensional case? Okay, and that's going to be sort of what I talk about today. Are there any questions about anything I've said so far? Okay, well, in the two-dimensional case, this problem had attracted considerable interest for some years. The problem was called the simplicity conjecture. We answered the question in some recent joint work with Vincent Humiliere and Soban Seyfedini. So in the two-dimensional case, we showed that the group is not simple. One interesting feature of our proof is that we used tools from symplectic topology. So that's sort of one reason that I want to emphasize that these are homeomorphisms. So part of the challenge of the problem is trying to use tools from symplectic topology to study homeomorphisms instead of diffeomorphisms. Okay, so before I get into our proof, I want to give more background about Fati's work, and in particular, what fails in dimension 2. So Leroux had written a beautiful paper, actually, about Fati's work and what happens in the two-dimensional case. And the key has to do with what's called fragmentation, which is a much used concept in this kind of story. So what is fragmentation about? Well, what Fati shows is, let's imagine that I've normalized my disk to have volume 1. So Fati shows that if the dimension is at least 3, if I'm given an arbitrary element, then I can write it as a product of 2 other elements that are supported on disks of smaller volume. So in this case, the volume is 3/4. And what Leroux does in his paper is he shows that this kind of idea is really at the heart of this problem about the two-dimensional case called the simplicity conjecture. So it's known that this particular fragmentation property fails in dimension 2, but Leroux showed that essentially there's a whole family of fragmentation properties. I won't give the precise definition unless asked, but there's a whole family of fragmentation properties. For example, this one is indexed by this parameter 1. And if any one of those fragmentation properties held in dimension 2, then this group in dimension 2 would still be simple. So to put this in perspective, our work shows that the group is not simple. So that means in particular that every one of these fragmentation properties fails. So I won't write out the fragmentation properties for you, but what you should imagine is that another consequence of our work is this strong failure of fragmentation in dimension 2 that contrasts the situation in higher dimensions. So to put this in some context for you, I want to talk a bit about the history of the problem and also talk about how some other of these transformation groups work out. So it's always useful to imagine that I'm working with a connected manifold here, and that I'm always looking at compactly supported maps, also in the connected component of the identity. Because again, if I want to find simple groups, I should always look in the connected component of the identity because that's a normal subgroup. So this question goes all the way back to maybe Ulam from the 30s, who asked, if I just look at homeomorphisms of the N sphere, is that a simple group? So here I'm not preserving any geometric structure or anything like that. And yeah, this was a question that he asked in his famous Scottish book. And actually in the 30s to 60s, the works of various authors, I've singled out some particularly important ones for this problem, showed that if I have any manifold, then this group of homeomorphisms is a simple group. So not just the sphere. So then you could ask what happens when I impose various amounts of regularity. So Smale asked in the late 60s, let's say I look at smooth maps instead of just continuous maps. Well, what happens? And then the works of various authors in the 70s showed that this is always a simple group as well. So now you could ask about what happens when you have some kind of geometric structure. So there the situation gets a little bit more complicated. It's maybe easiest to start with the case of volume preserving diffeomorphisms. So here I'm looking at diffeomorphisms that preserve a volume form. So it was known that this cannot be a simple group because there's a so-called flux homomorphism. Those of you who are symplectic geometers will be particularly familiar with it. So the group cannot be simple because it admits, at least in general, because it admits a homomorphism, which often is non-trivial. And so then in particular, you can take the kernel of flux. On the other hand, what Thurston showed is that if the dimension is at least 3, then the kernel of flux is a simple group. Okay, what about in the symplectic case? Well, you still have this flux homomorphism. But what Banyaga showed is that if the manifold is closed, then the kernel of flux is simple. On the other hand, if it's not closed, there's another homomorphism that some call the secondary flux or the Calabi homomorphism, and the kernel of that is simple. And we'll return to this Calabi homomorphism relatively soon. Okay, what about the case of volume preserving homeomorphisms? Well, that gets into Fatih's work. There's a sort of dual to flux called the mass flow homomorphism. And what Fatih showed is that if the dimension is at least 3, then the kernel of mass flow is simple. But before our work, the two-dimensional case had long been quite mysterious. I guess I've recapped the history for you, but let me just emphasize some differences. What we're saying is that the two-dimensional case really is more wild. So it's not simple. We're telling you the group is not simple. But on the other hand, it's not simple because of some geometrically constructed homomorphism, like flux or something like that. In these previous cases where there was geometric structure, you had something like the flux homomorphism, and okay, it's not simple. But we're saying it's not simple for some more strange reason. And in fact, in this previous paper that Leroux wrote, Leroux pointed out that if the simplicity conjecture failed, then the situation would be radically different from the situation for diffeomorphism groups, because you'd have, quote, lots of normal subgroups. So again, Leroux gives a precise definition, But I guess what I want to say is that in our case, what one finds is that there's not even in particular a sort of canonical normal subgroup that's obstructing simplicity. Rather, there are lots of possible ones that you could write down, and it seems to be a rather strange state of affairs. Are there any questions about any of that background?
Yeah, maybe if I can ask a question. When you say lots of, I mean, is this maybe referring to the fact that, so you have mentioned earlier that the rule work that they said there was if simplicity fails, then there's fractionality, or sorry, I forget the word you use.
Yeah, I went back to
fragmentation. Fragmentation fails for every row. So is there some statement along the lines that if fragmentation fails for a given row, then from that given row you can construct a row normal subgroup?
Yeah, that's actually absolutely correct. That's exactly what LaRue does. So for every row, you can construct a normal subgroup that measures the failure of the particular fragmentation property to hold. What LaRue does is he defines various fragmentation norms, and you can look at various growth rates in these fragmentation norms, and you get various normal subgroups that way.
So this result of rule, then it seems that there's an extremely strong dichotomy. So either you have no normal subgroups, or all of a sudden you have oh no, sorry, no, you don't necessarily have tons of them, because in principle it could fail for a single row for fragmentation in principle.
Right. But once you know that the simplicity conjecture, so the phrase simplicity conjecture is sort of a funny phrase, because if it's true, that means the group is not simple. So So this gets this gets into what you're saying. So if the simplicity conjecture is true, meaning that there is at least one normal subgroup, then LaRue's work comes in, and you learn that this fragmentation property fails, and in particular, you learn that there are lots and lots of normal subgroups. So it's along the lines of what you're saying, actually, that once you have one normal subgroup, LaRue's work tells you that you have lots and lots of them. But it's even sort of more than lots in a quantitative sense, because, let's imagine you had one of them and its quotient was R. You could always pull back, just some subgroup of R, and you'd get another one. And so it's actually often true that you have lots of normal subgroups, but in some precise way, you get kind of a ton of them. So it's a little hard to make exactly precise what LaRue is saying, but maybe as someone who's worked on this problem a lot, what I would say is that there's not really a canonical one once you have one, and in the diffeomorphism case, any one parameter family, most of the one parameter families of normal subgroups generate the whole group, whereas in the homeomorphism case, you have one parameter families staying in that aren't the entire group. So yeah, are there more questions while we're stopped? Okay. Well, I now want to tell you about some of the ideas of the proof. Okay, so the proof really has to do with this Calabi homomorphism that I was mentioning before. And so we want to say a bit more about how this works. So, well, okay, so earlier I said that if you look in the two-dimensional case for diffeomorphisms, then you get something that is not a simple group. And I said that that's because of the existence of this Calabi homomorphism. So let me now explain how this Calabi homomorphism works. So as is well known to symplectic geometers, if I have a compactly supported diffeomorphism of the two-disk, I can write it as the time one flow of a Hamiltonian, possibly varying in time. And in addition, I can demand that the Hamiltonian is 0 near the boundary, since the map is compactly supported. And so what you could attempt to do is to just integrate the Hamiltonian to get some invariant of the map. And what's cool is that this actually works. In other words, the potential problem with this is that there could be many different Hamiltonians whose time one flow gives you the map phi. And indeed, that there can be, but they all have the same integral, and that's this Calabi invariant. And once you know that, it's not hard to check that this is actually a homomorphism. So in particular, the group can't be simple. But crucially, this depends on on some smoothness of the map. If you have a C1 map, you can do this, but if you have a continuous map, it's not at all clear in what sense you could potentially write it as a time one map of a Hamiltonian. Okay, so this summarizes the situation in the smooth case. And remember earlier I was saying that Banyaga showed that the kernel of Calabi is itself simple. So more or less, Calabi is the only obstruction to the diffeomorphism group being simple. It's also nice to get some intuition for Calabi. So the definition I gave in terms of Hamiltonians is quite nice in practice, and it's fast, but it doesn't give you so much geometric intuition of what the map is measuring. It's nice to think of Calabi as measuring the quote average rotation of the map. So what I can do is, let's say I've written the map as a time one flow of some Hamiltonian. What I can imagine doing is I can imagine taking two different points in the disk and looking at how much they rotate around each other as time goes from 0 to 1. That's this variation in the argument part here. And then I can integrate that out over all possible choices of 2 points on the disk. And it turns out that this actually makes sense. I get a well-defined integral, and that's what this Calabi homomorphism is measuring. Okay, so in other words, in the diffeomorphism case, you get an obstruction from the average rotation of the map. All right, but we're interested in the homeomorphism case. And so how could we do this? Well, there's a naive idea that one could try to do. Namely, if I'm looking at the group of homeomorphisms, the group of diffeomorphisms does sit as a dense subgroup. It's dense in the C0 topology. So you have a homomorphism on diffeo, and you could try to extend it to homeo. However, you run into a fundamental problem with this, which is that Calabi is not, in general, a C0 continuous map. And there's a very nice example illustrating this that had been well known, prior to our work. So what you can do is you can take Hamiltonians, say, supported on disks of radius 1 over n around the origin, but integrating to 1. And so by our previous definition of the Calabi invariant, the Calabi invariant of their time one flow is always going to be 1. But on the other hand, in the C0 topology, the time one flow is going to be converging to the identity, right? Because it's supported on disks of smaller and smaller radius. And of course, the Calabi invariant of the identity is just 0, because that's the time one flow of the 0 Hamiltonian. So that's the kind of problem that comes up. You have a homomorphism defined on a dense subgroup, but it's not continuous in the natural topology, and you want to try to extend it to the full group. Are there any questions about that? So this is a problem that symplectic geometers had thought about for a long time, and made various proposals that had various degrees of success, but couldn't fully solve. And what we did is we built on these proposals with some new ideas coming from a particular kind of Floor homology called periodic Floor homology. So the basic idea here is to try to prove a kind of while law, or if you find that a fancy, if that's too fancy of a phrasing, to try to prove some kind of asymptotic formula. So maybe look at the third bullet point first. The basic idea is to try to prove some kind of asymptotic formula, recovering this Calabi homomorphism, which is not C0 continuous, from some invariants which are C0 continuous and extend to the homeomorphism group. And that's what we used this periodic Floor homology to do. So more precisely, what we do is for each diffeomorphism, we define a sequence of just real valued invariants that we call these PFH spectral invariants. The PFH comes from the fact that we're using periodic floor homology. And what we do is we show that each of them are C0 continuous. In particular, we show that each of these invariants extend to the homeomorphism group, but they're also rich enough to recover the Calabi homomorphism in their limit. Now, a few remarks here. This conjecture about recovering Calabi through the limit of these PFH spectral invariants was originally conjectured by Michael Hutchings. And in our paper, we only proved it for certain diffeomorphisms. Soon enough, I'll say exactly what those diffeomorphisms are. But we proved it for enough diffeomorphisms to get things to work. In a later work with Boyu Zhang and Rohil Prasad, we actually proved Hutchings's conjecture in full generality. And in another later work, at the same time as this first mentioned later work, Hutchings himself, together with Oliver Etmar, also have proved this conjecture. At any rate, for all diffeomorphisms. Okay, so are there any questions about the general approach then? In the next part of the talk, I'll fill in some details.
Yeah, I want to ask, so each individual CD is not a character, right? So it's not a homomorphism, it's just that the asymptotic is. Is that right?
Right, that's a great question, indeed. So each individual CD is not a homomorphism. It is probably the case that they are what are called quasimorphisms. If you know much about quasimorphisms, so they're within bounded distance of a homomorphism. However, that's work in progress. That's not actually known.
I see.
But yeah, indeed, each individual CD is not a homomorphism. Are there any further questions? Okay, so now I want to try to, so that was just sort of an impressionistic sketch of how we want to approach the problem. Now I want to go into more detail into the argument. So if you'll remember, what I said earlier is that we don't actually construct some natural homomorphism. Rather, we just write down a normal subgroup for you, and there's not necessarily a particularly canonical one to write down. But the one that we wrote down was the subgroup that we call the subgroup of finite Hofer energy homeomorphisms. So let me try to digest this for you. The idea here is to try to take concepts that are defined for diffeomorphisms and attempt to extend them to homeomorphisms. And so one such concept is this Hofer norm, which let me spell it out. So if I have a Hamiltonian, then I can look at its so-called one infinity norm, which is just given by the variation in the Hamiltonian, that's the infinity part, and then I integrate it from 0 to 1, because after all, my Hamiltonian might depend on time. And that's something that I can associate to Hamiltonians. I can associate that norm to maps by just taking the most efficient Hamiltonian that generates the map as a time one flow. And it was an insight of Hofer that this gives a very interesting metric on the space of Hamiltonian maps. Okay, so now we want to attempt to extend this to homeomorphisms, and we do it as follows. So remember that the diffeomorphisms are dense in the C0 topology in the space of homeomorphisms. And every diffeomorphism can be written as a C0 limit of a homeomorphism. So what I do is I say that a finite Hofer, that an arbitrary homeomorphism has finite Hofer energy if there's a way to approximate it in C0 such that the Hofer energy of the diffeomorphisms is not blowing up. So more precisely, I demand that there's some constant m such that the one infinity norm of these Hamiltonians is bounded by n while I approximate my map phi in C0. And okay, so that's some condition. We show that it actually gives you a normal subgroup. That's not so hard. I mean, if you know Hofer geometry, it's about a one-page calculation that it gives you a normal subgroup. what's very hard is showing that it's actually proper. That's sort of 99% of our work. And the only place where we use these spectral invariants is showing that this is not the entire group. So I want to see if you have any questions about the construction, since this is one of the more busy slides. But first, let me just make some remarks. So as I mentioned earlier, many symplectic geometers had thought about this problem over the years, especially as a kind of test case to what degree symplectic techniques can be used to study homeomorphisms. And a very influential paper on this subject was written by Owen and Mueller, where they propose a somewhat similar approach. They construct a different normal subgroup called the group of homeomorphisms, they run into the same problem, that it is definitely normal, but it's not so easy to show that it's not the whole group. At any rate, our group contains their group, and later we show that our group is proper. So in particular, their group is proper as well. So that's kind of a remark for people who are quite interested in this circle of ideas. Maybe the second remark is probably of broader interest, which is that our subgroup contains the commutator subgroup of homeo. So to put that in some perspective for you, remember earlier I was saying that if you have a normal subgroup that's proper, you can try to quotient out by it and get something interesting. Well, what I'm saying is this contains the commutator subgroup. So in particular, its quotient is going to be abelian. One also learns from this that the group is not perfect, which had been something that people wanted to know. So are there any questions about the definition of our subgroup? Okay. So the takeaway from the previous slide should be that the really hard part is to show that this group is not the whole thing. Or to put this differently, I need to find some homeomorphism that has so-called infinite Hofer energy. In other words, no matter how I approximate it in C0, the Hofer norm of the approximating diffeomorphism needs to be blowing up. And so a basic observation that motivates what we're doing is that the 1 infinity norm of a Hamiltonian is bounded from below by the Calabi invariant. I mean, this is not hard to see. Remember, the Calabi invariant is just the integral of the Hamiltonian. So if I'm looking at this 1 infinity norm, it bounds the total integral from above. So if you take this philosophical point of view that we want to find a homeomorphism that has infinite Hofer energy, then what the lower bound is telling you is that to do that, we should try to look for a homeomorphism with so-called infinite Calabi invariant. And then remember that this Calabi invariant intuitively is measuring the rotation of the map. So what this slide should be telling you is that in order to show that the subgroup is proper, we want to find some homeomorphism that has provably infinite rotation to it. That's the idea. Are there any questions about that philosophy? Okay, well, so armed with our idea that we want to find something with infinite rotation, we should start to talk about a particular class of maps called twist maps. So this is a rather simple class. These are just maps that preserve the radius. They're maps of the disk. And they rotate, but they can rotate by an amount that changes as the radius changes. So one can encode them in a function just of the radius, which I like to draw. It's convenient for technical reasons to study the so-called monotone twists, which are the ones where this function is just decreasing. So here's such a function, and this is the map that it generates of the disk. And it, you can check that this is an area preserving map. And if the function is 0 near 1, then it will be compactly supported as well. So now we have a nice class of maps for trying to get at this idea of infinite rotation. And okay, we should try to really get it to rotate fast. So what we do is we define a special class of twist maps by, so it might be a little bit easier to, what I've done here is I've reviewed for you the definition of the twist map on the first part. And now it's helpful to think about what's going on here. So we can define a class of maps to be infinite twists if they're twist maps away from the origin, but if the function that is parameterizing the amount of twist is blowing up as I reach the origin. Essentially, I want this function to be blowing up very fast. How fast? Well, remember, I wanted to have infinite Calabi invariant. So if I take one of these smooth twists, I can just compute its Calabi invariant from the formula that I gave you. And it turns out to be given by this integral. It just is what it is. So if this integral is diverging, which will be the case if f is blowing up particularly quickly as I reach the origin, then on the level of philosophy, I expect this to have infinite Calabi invariant. And so it seems like a good candidate to study for properness. And that's what we do. We show that any twist map like this, satisfying this integral condition, indeed is not in this subgroup of finite Hofer energy homeomorphisms. So I think I have a picture for you here. Right, so here's my twist map again, and I should think of my function as just blowing up. So what I do is I twist, and I twist more and more and more and more. And as I zoom in on the origin, I'm twisting a lot. Now I have to say where the origin goes. So I just send the origin to itself. And that will give me a homeomorphism, but not a diffeomorphism. And then the claim is that that actually has infinite Hofer energy. So in particular, that this group of finite Hofer energy homeomorphisms is proper. Are there any questions about that sort of picture? Okay. Okay, so now, how are we going to do this? So I guess I should say what the hard part of this is. Maybe I'll go back one slide. So we have this infinite twist. It certainly looks like it should have infinite Calabi invariant, but remember that being part of our subgroup F homeo just means that there's some way to approximate you such that your Hofer norm is not blowing up. So certainly in the most obvious way to approximate this by smooth maps, the Hofer norm is blowing up. The most obvious way to approximate it would be just by rotating smoothly for a long time and then close to the origin, just continuing with what you're doing. But what we have to show is that no matter how one approximates you in C0, inevitably the Hofer norm must blow up. And that's a hard problem where the floor homology ideas seem to be essential in one form or the other or another. Okay, so the argument goes something like this. So we want to show that this infinite twist is not in F homeo. So what we'll show is two different parts. The first part will be that if I am in F homeo, then my spectral invariants grow at most linearly with D. On the other hand, we'll show that the infinite twist has superlinear growth in D of its spectral invariants. So in other words, the argument is some kind of growth rate argument of these spectral invariants. The ones in F homeo grow at most linearly, is what we show. And so on the other hand, if we can just find a single example with superlinear growth, then we're done. So that's how we do it. Okay, well, so now let me tell you a little bit about how we prove these different properties. Okay, so the first property, remember, is that if I'm in...
Wait, can I ask
oh yeah, please.
a question?
Sure.
The last statement you made seems to suggest that maybe F homeo is the subgroup or subset of the compactly supported homeomorphisms on which the Calabi homomorphism extends to. I mean, is that...
Right, that's a great question as well. So later in the talk, I'll state some open questions. We actually don't know whether or not the Calabi homomorphism extends to F homeo. You could attempt to extend it by taking something like the limit of this map. Of course, we don't know whether the map has a limit. You could try to extend it by taking say the lim sup of this map, that would actually be an extension of Calabi, but the problem is we wouldn't know whether or not that's a homomorphism. We actually don't know if Calabi extends to F homeo. Earlier, I was talking about this O Mueller subgroup, hameo. We do show that Calabi extends to hameo in a later work. It's a bit of a mystery. I'd actually like to know whether or not Calabi extends to F homeo. But I will say that when we were thinking about this group, we were actually more thinking in terms of this aforementioned Hofer geometry. So for us, this is supposed to be the largest normal subgroup on which Hofer's geometry is meaningfully defined. Because, you know, if you're in F homeo, you can define a norm by taking this idea of using like a Hofer norm. On the other hand, I think O and Mueller were trying to define a normal subgroup by defining a subgroup on which Calabi reasonably extends. Indeed, we were later able to show that Calabi extends to hameo. So it's a good question, but yeah, we just don't quite know whether or not Calabi extends, at least in a natural way. Yeah. Are there more questions? Okay. All right, so I want to say a little bit about how the arguments for both part A and part B go. Okay, so remember A was showing that if you're in F homeo, then you have at most linear growth. And it turns out that this follows in a rather formal way from a property which is known to hold for other kinds of spectral invariants called Hofer continuity. So what does Hofer continuity say? It says that our PFH spectral invariants, our new spectral invariants, are actually Lipschitz in the Hofer topology, and they're Lipschitz with an explicit Lipschitz constant, namely D. So in other words, if I want to bound the distance between two my D spectral invariant of H and K, then it's bounded from above by just the one infinity norm of H minus K times this explicit constant D. So to put this in some context, spectral invariants have a long history in symplectic topology, and many of them satisfy some kind of continuity property like this. So we had to show that our new spectral invariants satisfy this property. And the appearance of the D here is somewhat of a new phenomenon, because in sort of previous work, people had often studied, like, say, one spectral invariant, whereas we have this whole sequence of spectral invariants. At any rate, once you have Hofer continuity, then you learn that A is true rather easily. Because in the context of A, I know that, you know, something you have to check is that the spectral invariants of the identity vanish. So if I let K just be the zero map here, I'm just getting now the size of CD of phi1h, and this is basically telling me that it's bounded from above by D times the Hofer norm of H. So more precisely, if I take my map phi and I approximate it in C0, then the Hofer norm is also staying close, and so you get the at most linear growth. So in other words, if we can prove Hofer continuity, then A follows relatively simply. Are there any questions about that? Okay, so depending on the time, I will say more about how we do prove Hofer continuity. Okay, how about B? B said that the infinite twist grows superlinearly with D. So maybe I should first say what the philosophy is. Remember, Hutchings's conjecture says that the limit of CD over D should give Calabi, and also philosophically, we're saying that the Calabi invariant should be infinite. So we just want to try to make this philosophy rigorous. And we will indeed do it by, to some degree, proving Hutchings's conjecture. So the first point is just a general monotonicity property, which says that if I have two Hamiltonians, H and K, and one is smaller than the other, then the same comparison holds for the spectral invariants. So now what you can do is you can do this naive approximation of the infinite twist by smooth ones and get something meaningful from that. So in a minute, I'll show you a picture which will help understand this. But what we do is we approximate the infinite twist with some smooth twists in a monotone way that allows us to use this monotonicity property. And we prove Hutchings's conjecture for the smooth twists. So maybe I'll show you a picture first and then come back to this slide so that you get a good picture for what's going on. Okay, so F is our infinite twist, and our argument is an argument about approximating F by smooth monotone twists and proving Hutchings's conjecture for the smooth monotone twists. So here's how our approximation scheme works. The smooth ones just come by following F and then just continuing what you're doing on an interval of size 0 to 1 over I. Okay, so that's what the FIs look like. So what I'm saying is, okay, so we wanted to look at CD of the infinite twist divided by D. By the aforementioned monotonicity property, we get that this is bounded from below by the smooth ones over D. And so now if you prove Hutchings's conjecture for the monotone twists, what you get is that if I take the limit in D for a fixed I, then that's converging to the Calabi invariant. So in particular, what I get when I combine these two inequalities is that my CD over D for the infinite twist is bounded from below by the Calabi invariant of each of these approximating smooth twists. But on the other hand, the Calabi invariant of these approximating smooth twists is blowing up because it's tracking more and more closely this map F whose integral is blowing up. And so that's basically the proof, namely the Calabi invariant of the FIs is going to infinity. And so what I learned from this is that the CDs of the infinite twist must be growing super linearly as well. So are there any questions about that general argument? Just to recap it in terms of intellectual debt, what I'm claiming here then is that if I prove this monotonicity property, which is again something that is often true for spectral invariants, and if I also prove Hutchings's conjecture for the class of monotone twists, then I learn this superlinear growth property just by approximating from below. And so then what remains to be done is to prove Hutchings's conjecture for monotone twists and also to prove this monotonicity property. And as I said, in later work, we actually proved Hutchings's conjecture in total generality. Hutchings himself and his collaborator did as well. All right, so are there any questions about that? Okay, so I've stated the intellectual debt that I've brought up here as a to-do list. So if you now want to take these arguments and make them rigorous, you now have to do the following. Well, first of all, you have to define PFH spectral invariants. You have to show that they're C0 continuous, they're Hofer continuous. You have to show this monotonicity formula. You have to prove Hutchings's conjecture. And then what I've shown you is that once you've done these three things, then you can put it together as I've explained, and you will have shown that the group is not simple. And that's what we do in the paper. Okay, so what I next want to tell you then is just how these PFH spectral invariants are defined, and at least an impressionistic sketch. And you'll see that at this point, I've reached what I call the bonus slides. Namely, this is a little bit like one of these choose your own adventure books. I wasn't entirely sure how many questions there would be and how quickly we would go through things. So we can go through this stuff until it's time to go. I mean, I think I have about 9 minutes left. And we can also go through it in any order. The three things can be done independently of each other depending on interest. So
you have about 15 minutes, actually. We started a bit late, so please.
Oh, we started late. Okay, well, sure. Well, so then maybe we can even go through all three. But But at any rate, these next three sections can be done in any order. The first part tells you what these PFH spectral invariants are. The second part gives you some remarks on how you prove Hofer continuity and Hutchings's conjecture. And the third part has to do with, for example, questions that were being asked earlier about quasi-morphisms and extending Calabi-Yau stuff. So we can go through them in any order. I guess if I hear no preferences, I'll just go in the order in which they actually come. So if anyone wants to speak up, now would be the time. Okay, so let's just do them in the order that they come. Okay, so I next want to tell you what are these PFH spectral invariants, and the definition is somewhat complicated, so I can give only an impressionistic sketch. Well, okay, so the first part is that they use this so-called periodic Floer homology, and that is most naturally defined for closed surfaces. So it's really a special thing about dimension 2, and it's easiest to define it for surfaces, for closed surfaces, I mean. We have a disk, but the way we get around that is quite simple. You can just embed the disk as the northern hemisphere of your 2-sphere. And remember, our maps are compactly supported. They're the identity near the boundary. So they extend by the identity to all of the 2-sphere. And so then we can use this periodic Floer homology of the 2-sphere, which I have to tell you a bit about how it works. Okay, so how does the periodic Floer homology of the 2-sphere work? Well, the general idea here actually is to try to get invariance of maps on a surface by using 3-manifold theory. So what I want to do is I want to take this map of the 2-sphere and build a 3-manifold from it, and then try to use ideas for studying 3-manifolds to learn something interesting about the map phi. And the natural way to do that is with the well-known mapping torus construction. But so just to fix notation and to point out some geometric structures on the mapping torus, what I can do to build this mapping torus is I just take the product with an interval, and then I glue the two pieces of the boundary together via the map phi. And this has some nice geometric structure on it for our purposes. First of all, it has a canonical vector field, R, which just points up in the d by dt direction. And it has a nice canonical 2 form as well, omega phi, which is just induced by the area form on the disk, because this is an area preserving map. So for those of you who are kind of specialists in this point of view, basically the pair of this vector field and this 2 form correspond to what one would call a stable Hamiltonian structure. And the R here comes in analogy with the Rabe vector field from contact geometry. So if you have a contact form, you always get a canonical vector field, the so-called Rabe vector field. Now, this vector field R is not, in general, going to be a Rabe vector field for a contact form, but it does exist. And the right way to think about it is as the canonical vector field for a stable Hamiltonian structure. But if you're not a specialist, just think of this as a canonical vector field on the mapping torus and a canonical 2 form. Okay. All right, so now I can define this periodic Floer homology for you. So it's going to be a vector space over the field of 2 elements, and it's going to be our input, which will allow us to define spectral invariance. So what it is it's a homology of a chain complex. So I have to tell you, what the underlying vector space is, this PFC, and then I have to give you a differential which on the vector space which squares to 0. Okay, so the chain complex, this PFC, it's going to be given by sets of closed orbits for the vector field. So more precisely, what I should say, imagine, is that a generator of this PFH chain complex is a finite set of pairs alpha I, mi, where the alpha i's are embedded periodic orbits, and the mi's are positive integers, which I can think of as like covering multiplicities. So basically what I'm doing with this pairing is I'm separating out a closed orbit into a simple piece, and then it's covering multiplicity. And a rather strange feature of the definition, which is hard to explain to non-specialists, is that if I have hyperbolic periodic orbits, that I don't want to allow any multiple covers. So maybe we won't go into that too much now, although I could say more in the question and answer period. So to sum up then, this chain complex is freely generated over Z2 by finite sets of periodic orbits of this vector field R on the mapping torus, with this condition that I don't want to allow multiply covered hyperbolic orbits. Are there any questions about the definition of the underlying vector space? Okay, well then I have to define a chain complex differential for you. So the differential comes by counting pseudo-holomorphic curves. You probably know that pseudo-holomorphic curves are objects that make sense in symplectic manifolds. Well, here I have, a mapping torus. It's a 3-manifold. It's certainly not symplectic, but it turns out that if I take its product with R, then I can use the canonical 2 form from the previous page to build a symplectic structure on this 4-manifold. I can call this a symplectization of the mapping torus. And then I can count holomorphic curves in this symplectization. I'll show you a picture in a second. But the point is that if I have a generator alpha and I want to know what D of alpha is, it's going to be a sum over orbit sets beta I. And the coefficient on beta I is just going to be a count mod 2 of the J holomorphic curves in this symplectic manifold going from one orbit set to the other. I'll show you a picture. But one important point is that I don't want to count all the curves. I mean, for example, in order to count them in the first place, I better hope that there's only a finite number of them, say modulo translation, because I only ever count modulo this translation in the R direction. So I want them to, to single out some particular curves. And it turns out that the right way to do this is with this so-called ECH index, which is beyond the scope of the talk. But what it does is if I look at just the ECH index 1 curves, it singles out some particularly interesting, essentially embedded curves. And it also forces them to be rigid modulo translation in this R direction so that I can meaningfully count them. So here's a picture that's good to keep in mind. Okay, so I have an orbit set alpha. That's one of my generators in my chain complex. I want to know what D alpha is. It is just a sum on orbit sets beta of the mod 2 count of pictures like this. So here I have a holomorphic curve in R cross my mapping torus. As I go to the positive direction in my mapping torus, it's asymptotic to alpha. As I go to the negative direction, it's asymptotic to beta. The curve could have genus. It could have multiple components, but it has to have ECH index 1. In particular, the interesting components must be embedded. They can't intersect each other. So that's an impressionistic sketch of this periodic floor homology. Are there any questions about that? Okay, so so remember these spectral invariants, they were these C sub Ds. So where do the Ds come from? Well, this periodic floor homology has a splitting into subcomplexes where I just look at orbit sets of degree D. So, one of these orbit sets alpha has a degree just by looking at how much its projection goes around the S1 factor for my mapping torus. And my curves have to preserve the degree because they give homologies between the orbits. So the group splits into pieces of different degrees. And that degree D is what's parametrizing the C sub Ds. So that's just a vector space, but I'd like to use it to define these spectral invariants. And remember, these spectral invariants are taking values in R. So the key point is that it's not just a vector space, it comes naturally equipped with R-valued filtration called an action filtration. So what I can do, I've been a little vague with the notation for time reasons here, is I can integrate this canonical 2 form, omega phi, to get a real valued number called the action. And there's also a grading which comes from this ECH index. the ECH index gives a grading such that the differential decreases the grading by 1 because it counts ECH index 1 curves. So, so now I can define this CD sub phi. What I do is I look in degree D and grading 0. Okay, so it turns out that the homology is non-zero there, at least if D is even. I'm just doing the case where D is even. But it turns out that the homology is non-zero there. And in fact, the piece in grading 0 in degree D is just Z2 as a vector space. So it has a unique element, and I can look at the minimum action required to represent it. Okay, what might that look like? Well, remember, this is the homology of a chain complex. So there could be various, so a particular representative is going to be sum of actions of orbit sets. And I've just explained what the action of each orbit set is. But there, since it's the homology of a chain complex, there could be multiple different representatives, and I take the most efficient one. And those are my spectral invariants, C sub D. So I guess one more remark about this, you might note I did something slightly subtle. I went from PFH to this PFH twiddle. That's because in order to define spectral invariance, you have to do what's called twisting the complex. I've suppressed the exposition of the twisting of the complex for time reasons, but basically it involved adding this second parameter Z. So earlier I just had orbit sets alpha, but in the twisted complex, I want to allow orbit sets alpha together with a homology to a distinguished degree D reference cycle, which in my case, I just take to be the D cover of just the closed orbit over the South Pole. So I don't want to go into that too much now, but if people have questions, I could talk about it some more. But at any rate, if you're learning about this for the first time, it's just one has to twist the complex to get this filtration. But what's really important is this idea that the two form gives you some R-valued filtration on the complex, and you can use that to define your spectral invariance. So I was sort of planning to stop here. I think this is actually a good place to stop. Peter, you're moderating. I don't know quite when we started, but I think now is probably a good place to stop. And then others, if you want to ask questions, I can talk about the other parts of the other bonus slides and stuff.